when two planes are parallel, then their respective normal vectors must be also parallel. And if they are orthogonal, then their respective normal vectors will be orthogonal. So we can use this property to identify which of the following ones are parallel and which ones are orthogonal or identical. So let's identify quickly each of the following the normal vector, and then because that's pretty that will be the useful information that we need. So for the first one, let's use this notation. Let's zoom in a little bit here. So I'm going to use n to denote the normal vector. So n sub q will be this. And hopefully you can read that off here. So it's 3, negative 2, and 1. 3, negative 2, and 1. And obviously QR will be negative 1, 2/3, and negative 1/3. And actually, by doing a little quick mental math here, do you see that this NQ is actually 3 times of this NR? For some reason I wrote it as QR, supposed to be NR. N represents the normal vector. So we can quickly see that NQ is 3 times of the NR. Therefore, I do know that Q and R must be parallel. Now let's continue to find the other normal vector. NS is going to be negative 1, 2, and 7. And NT is 3/2, negative 1, and 1/2. Now, for the last one, because it's quite nice, the numbers are nice. If you multiply by 2, multiply the whole vector by 2, we actually see that we're going to get NQ, right? So in other words, NQ is actually also equal to 2NT. Because of that reason, I know that these 3 vectors are parallel. Now, let's check one quick thing here. If we check NQ dot NS, let's look at the dot product of these 2 normal vector. So which means 3, negative 2, and 1 dot negative 1, 2, and 7. Let's do the algebra. So it will be negative 3 minus 4 plus 7, which is equal to 0. This means NQ is actually orthogonal to NS. From here, we do know that the plane S is actually orthogonal to plane Q, and because QRT are parallel, which means S actually is orthogonal to all those 3 planes. So therefore implies S orthogonal to all those 3 planes Q, R, and T. Now, so we've done some basics. Let's see how we can find an equation of the plane when you're given a point and a parallel plane. So, for instance, sometimes it might be nice to see an example. So if I say give you a point, this one, negative 2, 4, and 1, this is a point, and that the plane is parallel to, let's create a plane. So say this guy, 3x minus 2y plus z equals 4. Then how do you find a plane that's parallel to the given plane and also passing through the point Q? From the plane equation, we do see that the normal vector is equal to 3, negative 2, and 1. and we have a point, we have a normal vector because parallel planes, they have the normal vectors are parallel, so I can use this normal vector to find the plane equation. So the plane equation becomes this: 3 times x minus negative 2 becomes 3 times x plus 2, minus 2 times x minus 4, and plus 1 times x minus 1 equals 0. So this will be the plane equation that we can find that meets the requirements. So that's how we would find an equation of plane when a point and a parallel plane is given. Now, how about the line of intersection when two intersecting planes are given? So, for instance, again, let's call, say, this time let me call plane Q as this one, x plus 2y plus z equals 5. This is a plane, not a point. And let's say plane R is 2x plus y minus z equals 7. Now we notice, just do a quick checking, these two planes are not parallel because the normal vectors are not multiple of each other. So I know they're not parallel. You can quick check. The first one is 1, 2, 1. The other one is 2, 1, negative 1. You can see one is not parallel to the other, right? So therefore they must intersect. So now I'm gonna say let x, y, z be any point on both planes. And now, and these points must satisfy these two plane equations. So basically, you are looking for a point who is also on this plane and at the same time on this plane as well, right? So basically, you're looking for x, y, z so that these two equations are true. So we are looking for a solution for these two. You have only two equations, but there are 3 variables, which means more variables than the equations. And therefore, you have infinitely many solutions. So keep in mind that what do we want to find? We want to find the equation of the line. So in order for us to find the equation of a line, we need there are different ways. Method number one, you can find 2 points, right? And using those 2 points, you can determine a direction and use one of the points, and then you find the equation. So that's method number 1. Let's demonstrate that. So one way is to find 2 points. So I'm gonna let z be 0, and then I have x plus 2y plus 0 equals 5. The other one is 2x plus y equals 7, and then you can solve for xy. I'm going to use equation number 2 minus 12 twice of the equation number 1. If you do this, if you solve for x and y, I'll leave that for your exercise. And here's one solution: x equals 3, y equals 1. Okay. In other words, 3, 1, 0 is one of the points. You can find second point by, you don't have to let z be, say, 1 or 2. You could, but probably I feel that it might be easier. I just let x be 0. So when I let x be 0 from the Q, the plane equation, I'll get 2y plus z equals 5. And then from the R plane, so y minus z equals 7. So when I add these 2 equations, I get 3y equals 12, which means y is equal to 4. And then when I know y is 4, the z must be equal to negative 3 from the second equation. So the points that I have is 0, 4, and negative 3. Hopefully, now you know how to continue because you have 2 points. Therefore, the direction, the direction, say I'm gonna call this as point P, this as point, I use Q, I use R, how about I use say S. So PS is gonna be use S minus P, so negative 3, 3 and negative 3, which is 3 times negative 1, 1 and negative 1. I should use a vector notation, right? Vector notation. So I don't need to use this 3 because I just care about the direction. So this is the direction I use, and therefore the line is, okay, hopefully you still remember x, y, z is equal to, use a point. So the point that we have, I'm going to pick the point P, so 3, 1, 0, plus t times the direction, negative 1 and negative 1 and negative 1, 1 and negative 1. So therefore this is my method number 1, okay? Now another method is this. So method number 2, I always encourage you to think about more methods rather than just solve the problem using only one method, because we do know that so if you have 2 planes and they intersect with each other, and this is the line of intersection, and you're pretty sure that now say suppose this is the normal vector that's perpendicular to this plane, and this is another normal vector, the other normal vector perpendicular to this blue one is perpendicular to this plane. When we say the normal vector, this normal vector must perpendicular to all the lines on this plane, and this one, the blue one, same, it must be perpendicular to all the lines on that plane. The line of intersection, which is this green one, because it's on both planes, it must be perpendicular. This green one must be perpendicular to both these 2 normal vectors. I already have a point, and now I just need the direction of this green line. So how do we find the direction of this green line? Because it's perpendicular to those 2 vectors, so we can just simply find a cross product of these 2. So I'm gonna leave that to you to verify. And so find the cross product, which is after the algebra, it's going to be negative 3i plus 3j minus 3k. So if you factor out the 3, say I'm going to factor out a 3, okay, and then you're going to get negative 1, 1 and negative 1. So that's actually the same as what we just found previously. So use this point and use this direction vector, we can actually find the equation of the line. A quick recap. Here we learn how to check whether planes are parallel or orthogonal, and we also know how to find the plane equation for a given point and a parallel plane. More importantly, we know how to find the line of intersection of 2 planes.